Okay, so today what we're doing is we'll talk about AC circuits. Um, and so before we do this, let me review a couple of things about DC circuits. I'll draw a simple DC circuit. So here's a very simple DC circuit. Okay, so here's a source, and here's a resistor. You saw that the current in this circuit was given by voltage divided by the resistance. The power was given by V times I square R, or one more expression. Let's see, V, okay. So V square over R, okay. So the power in the circuit was given by that. All right, so what we'll do is that today we'll study an AC source, okay. So this DC source got replaced by an AC source, and what we will connect is, so this will be the most complicated circuit we'll consider. Resistance, a capacitance, and an inductor. We'll connect them in series, okay. And what we want to do is derive similar expressions to that of a DC circuit for this AC circuit, okay. The resistance, the generalization of resistance for a circuit is called impedance, denoted by Z, okay. And the impedance of this circuit, so it turns out that the impedance is a function of the frequency of this source, okay. And the impedance for that circuit is given by R square plus XL minus XC square. XL is the impedance of the inductance, or the resistance of the inductance, and that's equal to omega L. See, this is a frequency dependent thing. And XC is the impedance of the capacitor, and it's 1 over omega C. Okay. So again, so we will consider, we'll look at circuits with AC sources in them. We'll generalize the term. We'll see how to calculate the resistance of this circuit, which is called the impedance. Okay. And again, this is the most complicated circuit we'll consider. So for instance, you could connect those guys like so. Here's a parallel connection of the devices, okay, but we won't consider that, and there are many other combinations, okay. So the impedance of that series RLC circuit is given by that. The impedance of the inductor is omega L. The impedance of the capacitance is 1 over omega C. Impedance is the generalization of resistance, the term resistance, okay. All right, so in general, what we are interested in is the following. So here's an AC source, and here's a black box. This is the circuit, okay. What we are interested in is this AC source, the voltage as a function of time is given by Vmax sine omega t, and we will be interested in the current as a function of time, which will be Imax sine omega t minus phi, okay. So what this is telling you is there's a phase shift between voltage and current. What this tells you is that the current doesn't keep in step with the voltage, okay. So for a circuit like this, we'll be interested in two things. What is the amplitude of the current? What is that? And what is the phase shift? Okay. So those are the two things we're interested in an AC circuit. All right. So keep that in mind as we go through the slides. All right. So the three elements we'll look at as in an AC circuit are resistors, inductors, and capacitors. We won't consider diodes or transistors or any of the other stuff. You'll do that in more complicated in a circuits course at a junior or senior level. Okay, so we'll connect the three in series and we'll look at that. We'll look at the resonance in an RLC circuit, okay, and energy and so on. Okay, so let me show you an AC source. Okay, so here's a loop of wire placed between a magnet. And if you make this loop turn, and we've learned about several ways of making the loop turn. In a windmill, the wind turns the blades, which turns in turn turns this loop of wire. Okay. So you turn that loop of wire, and what you get is an AC voltage. Okay. So the work, and it takes work to turn the loop. That work is being turned into electrical energy. Okay, so that's what's happening. And if this loop is connected to the outside world like this, what you get is an AC signal like this. Okay. Let me show you the DC. All right, so that was an AC source. So again, here's an AC source. So this is what we are connecting to our circuit that I showed you. All right, so that's what this AC source is. And the voltage is given by the amplitude of the voltage times sine omega t. Omega is the frequency. Omega is 2 pi f, and in the US, the frequency is 60 hertz. Okay. In Europe, it's 50 hertz and so on. All right, so that's the signal we get. And out of your wall socket, you get 120 volts. So, and the peak would correspond to about 100, and the amplitude would correspond to 180 volts. Okay. All right, so that's the signal you're getting out of your wall socket. All right, so generators. So this was a generator that converts mechanical energy to electrical energy. So this is an AC generator. Devices such as light bulbs and toasters work equally well with AC and DC currents. Okay. So our motors are more easily adapted to AC currents. And electric motors, as you know, do 90% of our work. Okay. So that's what we're connecting. So here's the AC source. Here's the electrical symbol for the AC source. Here's a resistor connected to an AC source. Okay. So this voltage is described by that function. Okay. So you can use a sine or a cosine function to describe that. All right. So again, here's a general AC. Here's a general circuit. Here's one AC source connected to this circuit. The voltage provided by this source is Emax sine omega t. Emax is the amplitude of the voltage. And what we are interested in is the amplitude of the current coming out of this source, sine omega t minus phi. See, phi is called the phase shift. Okay. And if you connect a pure resistance to the circuit, this would be 0. If you connect a pure inductor to the circuit, this would be pi by 2, 90 degrees. And if you connect a pure capacitor, this would be minus 90 degrees. Okay. So what we're saying is phi. Okay, so what we're saying is for that circuit, the phase shift phi varies between plus 90 degrees and minus 90 degrees. When phi is 0, it's a purely resistive circuit. When phi is minus 90, it's a purely capacitive circuit. And when its phi is 90 degrees, plus 90 degrees, it's a purely inductive circuit. Okay. So we've connected a circuit like this, and these are the two things we want to know. What is the amplitude of the current, and what is the phase shift? And again, going back to, so we've connected to an AC source, we've connected this black box of a circuit, and of course, the amplitude of the current is just the amplitude of the voltage divided by the resistance of the circuit. So what is the Z value? The impedance of the circuit is what we are interested in. And again, phi tells you whether the circuit is a purely resistive circuit, is it a capacitive circuit, or an inductive circuit. Oops. All right, so here's the circuit. We want to know the impedance of the circuit. The amplitude of the current is the amplitude of the voltage divided by the impedance of the circuit. What is the resistance of the circuit? And the phase shift tells you what kind of circuit is it. If the phase shift is 0, it's a purely resistive circuit. If the phase shift is minus 90 degrees, it's a purely capacitive circuit. And if it's the phase shift is plus 90 degrees, it's a purely inductive circuit. And of course, the phase shift generally is between minus 90 and 90 degrees. Well, it's always between minus 90 and 90 degrees. But for most interesting circuit, it's somewhere in between. Okay. Now here's the deal. If the phase shift were either minus 90 or plus 90, no energy is being dissipated in the circuit. So meaning that it's not cooking anything. So for instance, your toaster doesn't have a plus or minus 90, your dishwasher doesn't have plus or minus 90. Anything that does work cannot have plus or minus 90 degree phase shift. Okay. All right, so again, this is the general circuit that's connected to this AC source. What we are interested in is what is the amplitude of the current and what is the phase shift. Okay. All right, so that gives you a brief overview of this chapter, and I will stop recording